接下来呢，我们就有请这个在芯片领域非常知名的专家。我们第3位嘉宾是 ARM 架构的主要设计者，也是我们智源研究院学术委员会的委员，是 Furber。我们先看一段他的介绍视频。
史蒂夫·福伯，计算机科学家、数学家和硬件工程师。现为英国皇家科学院院士、皇家工程院院士、欧洲科学院院士、英国计算机学会 IET、IEEE 会士。福伯教授在计算机系统结构、微处理器设计方面享有国际盛名，被誉为 ARM 架构之父。其主持研制的 ARM 微处理器是现如今广泛使用的手机、平板电脑等嵌入式设备中的核心芯片。目前，他主持开发的利用 ARM 微处理器构建模拟人类大脑的欧洲人脑计划，是欧洲迄今为止投入最大的专用超级计算机。福伯因其在计算机领域取得的卓越贡献，荣获 IEEE 计算机先驱奖、IET 最佳成就奖、大不列颠帝国司令勋章等终身荣誉。
好的 ，Hi Steve。
Good morning. Well, afternoon, I think, where you are.
Yeah, you can share your screen. Yeah,
Okay.
share your screen now. You can share the screen, the button.
Yeah.
Yes, the green one.
Okay. Can you see my screen?
Yes. Perfect.
So, should I proceed?
Yes, you said.
Yeah, it's okay. You can
All
start.
right. Okay, I will start. So, I'm Steve Furber. I'm Professor of Computer Engineering in the Department of Computer Science at the University of Manchester in the UK. And currently in the UK, we're still in some sort of lockdown, so I'm speaking from my home in the Manchester suburbs. My talk today is entitled Building Brains, Artificial and Biological Intelligence. And what I'm here to talk about is the project I lead at Manchester, which is called SpiNNaker, where SpiNNaker stands for Spiking Neural Network Architecture. And this is a massively parallel computer designed to support real-time models of the brain. As the previous speaker indicated, it's important for progress in AI that we understand more about the brain and use that to inform how we design our AI systems. But the current position is that we do not fundamentally understand how the brain works. So the SpiNNaker project is aimed at contributing to our understanding of the brain, and hopefully that will then feed through into better computers and AI in the future. So here's the outline of my talk. I'm going to introduce some historic reflections on interest in understanding the brain, then talk about the inspiration that has led to the SpiNNaker project. I'll describe the project itself, and I'll also then talk about the next generation of the machine, which is still in design phase, but should become available from towards the end of this year. So, 200 years ago, the lady pictured on this slide is Ada Lovelace, and she's well known in computing circles for being the assistant to Charles Babbage. Babbage was an engineer in early Victorian times who built and designed very early mechanical computing machines. And Ada worked with him, and she thought about the sorts of things those machines could do. She was one of the first people to think in terms of algorithms, and is viewed by many as the first person to think like a computer programmer. in her notes, she talks a lot about algorithms, but she also reflects on her interest in the brain. And in her notes, I've quoted some here, she says she has distinct hopes of one day getting cerebral phenomena, that means what we see about the brain, such that I can put them into mathematical equations. I hope to bequeath to the generations a calculus of the nervous system. Now, this was a very ambitious project 200 years ago, and even today, we are not close to being able to deliver a calculus of the nervous system. We still lack a fundamental understanding of how the brain works. 150 years later, this man came to Manchester. At the top left of the slide is a picture of a house which is quite close to where I live, about 10 miles south of the city centre of Manchester. And above the brick archway to the left, where the blue arrow is pointing, there is this plaque which says that Alan Turing, founder of computer science and cryptographer, lived and died here. And indeed, this is the house where Turing spent his last few years. He came to Manchester because Manchester had built the first machine to implement Turing's big idea from the 1930s of the universal computing machine. While he was in Manchester, Turing worked on a number of projects, but the most relevant here is expressed in this seminal paper with the title Computing Machinery and Intelligence. And this paper begins with the words, I propose to consider the question, can machines think? This paper was published in 1950, which was just 2 years after the Manchester machine ran its first program, which in fact was on June the 21st, 1948. And already 2 years into the history of operational computers, Turing is beginning to wonder about how far this technology might go. In this paper, he decides that the question, can machines think, isn't a good research question, and he turns it round into a test for human-like artificial intelligence, which he calls the imitation game, the subheading you see here. He called it the imitation game. We simply know it as the Turing test for artificial intelligence. Now, in this paper, Turing reckons that all that a machine would need to show human-like artificial intelligence, compared with the Manchester machine he came to use, was more memory. The Manchester machine had 128 bytes of memory, and Turing reckoned a gigabyte would be about enough to be able to imitate human intelligence. And in this paper, he predicts that by the end of the 20th century, machines might have a gigabyte of main memory. Indeed, this was a remarkable prediction when you think that the Manchester machine had just 128 bytes. And it was very accurate. It was around the turn of the century that a typical desktop PC would have about a gigabyte of memory. That PC would also be about 1 million times more powerful than the Manchester machine, but it would not pass Turing's test. And even today, no machine has convincingly passed Turing's test for human-like artificial intelligence. And there are various reasons why human-like AI has proved much harder than Turing and many people since him expected it would. But my personal view is that the reason that we found human-like artificial intelligence so hard is because we don't understand natural intelligence. We don't understand how the brain, which is the seat of intelligence, does its job. And that's why for the last 20 years, my research has turned towards trying to contribute to our understanding of brain function through building appropriate machines. So that leads me to my next topic, bioinspiration. And the two principal research questions which have driven my research for the last 20 years are shown here. We now have formidable computing resource available to us. Can we use this to accelerate our understanding of how the brain works? And as we learn more about the brain, can we use that knowledge to build better computers, where that better may be more efficient, more fault tolerant, or indeed more intelligent? Now, while we've been working towards these research questions over the last 20 years, there has, of course, been a parallel development in the use of neural networks in industrial AI. And here's a typical example of a simple convolutional network, the sort that's used for doing image classification. And the principle of this network is that an image is shown at the left-hand side, a picture of a cat, or here it's a face. And then this passes through many different neural layers, each with very large numbers of parameters, until at the right-hand side, there's a classification layer. And the classification layer says it's a cat or it's a face. If the classification layer produces the wrong answer, then that's an error, and the error is propagated from right to left all the way back up the network, adjusting the millions, sometimes hundreds of millions of parameters in the network until the network starts classifying that picture correctly, and then you can carry on. And in the early example of this, the Google Net learnt to recognize cats after being shown about 10 million pictures of cats. Now I contrast that with my 2-year-old grandson, who could see one cat and then recognize cats reliably for the rest of his life. So there's something fundamentally different about how artificial nets learn to recognize things and how biological nets learn. Now, of course, it's not a fair comparison, because the Google Net started with all of its parameters randomized, whereas my 2-year-old grandson starts with 2 years experience building a complex model of the world into which cats fit rather nicely. But even so, there's some big differences between how artificial nets and biological nets learn to perform similar tasks. If we look at a simple and abstract example of a brain circuit, this is a small section of cortex shown in quite simplified form, then what we see are some quite different features. For instance, it isn't a simple network that flows from the input at one end to the output at the other. Everywhere in this network, information is flowing backwards and forwards. Inputs come from different places, at different layers in the network. Outputs are taken out at different layers. So it's a much less linear and complex process. It's doing something very interesting, but still we do not understand how this basic cortical circuit works. And that's a major focus of research into understanding the brain, is to understand how the basic cortical circuit does its job. But we aren't there yet. Now, if you want to model an artificial network, then the kind of computer of choice is something like this. This is a powerful GPU. It's very good at dense matrix multiplications. Because artificial nets are currently dense, these map very well onto GPUs. This box consumes about 3 kilowatts of power, and training large networks uses a considerable amount of energy, which is of growing concern. But it's an effective way of training an artificial net. If you want to do something similar with a spiking network, which is more biological, then the standard computer that can do this is something like a high-end supercomputer. These are good at sparse matrix operations, which is important because biological networks are always very sparsely connected. You can now communicate with the kind of spikes that biological systems use. but the power consumption of the machine has gone from kilowatts to megawatts. On the other hand, there is special purpose hardware that has been designed specifically for modeling spiking networks, and this is characterized by having the memory very local to the computation, and then you can achieve much lower power levels. This will model spiking networks in biological real time, which is still not possible on a supercomputer, and the power has now gone into tens of milliwatts. So we saw kilowatts and then megawatts and now milliwatts. So this sort of hardware, which handles biological networks very efficiently, is of very great interest because of its energy efficiency characteristics. The example shown here is the IBM TrueNorth chip, but there are many other examples around of neuromorphic technology. Because of the obvious advantage of energy efficiency here, industry interest has been growing recently. IBM's chip I've already mentioned, Samsung has been using that, and more recently Intel launched a chip that they call a research prototype, so it's not a product, and this is the Intel Loihi chip, which is a very advanced piece of silicon for modeling spiking neural networks. As well as big industry, there are startup companies. Innovation is a spin out from ETH Zurich in Switzerland. Chronocam spun out of the Paris Vision Institute. Both of these are working on spike-based vision systems primarily. And in Manchester, a startup company called Mindtrace secured initial funding to create self-learning machines. These are based on spikes or event-based AI networks, and they are using the Manchester SpiNNaker machine as a development platform. So there is industry interest, but I would have to say that the current state of the art in spiking networks is that there is still no truly compelling demonstration of the viability of spiking networks in the commercial domain. Our focus at Manchester has been on contributing to brain science, and there the evidence is much stronger, but we're still awaiting the compelling commercial demonstration of the value of spiking networks. So now I'll move on to our particular project at Manchester, which is called SpiNNaker. And the goal we set ourselves about 20 years ago was to see if we could build 1 million mobile phone processors into a single computer and connect them in such a way that they could collectively implement spiking neural networks in biological real time. From the outset, it was clear that even with 1 million processors, we are not getting anywhere close to the scale of the human brain. In fact, optimistically, we may get to about 1%. Now, the mouse brain, conveniently, is very similar to the human brain, but 1,000 times smaller. So 1% of the human brain corresponds to 10 mouse brains. And now we have more realistic estimates. We could probably realistically model a network of about the scale of 1 full mouse brain. Again, using fairly simplified neural models, but basically modeling every neuron and synapse in the mouse brain. That's just about achievable with the present machine. The development of the machine started with the design of a silicon chip to do the neural computation. This chip incorporates 18 conventional ARM general purpose processing cores. These are small cores. They're not the big powerful cores that you find in the application processor in a phone. They are the small cores that do things like memory management and Bluetooth management. And these 18 processors sit on this 1 centimeter square die, and they're packaged with an industry standard memory chip in a 2 centimeter square ball grid array shown at the bottom left of this slide. And this is a component that we can then effectively tile a 2-dimensional surface with. So we take the SpiNNaker chip with its 18 cores. We can then tile these across the 2-dimensional surface of a printed circuit board. And the standard board that we've produced incorporates 48 of these packages, and that's 864 ARM cores. And these all connect chip to chip, and then board to board connections are made through high-speed serial links, and that allows us to build large machines. And we achieved our original objective of 1 million cores in November 2018. This machine, shown on the right, has been in continuous service under the auspices of the European Union Human Brain Project, initially at half size from March 2016, and then the full 1 million core size from November 2018. And this machine is accessible over the internet from anywhere in the world, and we have order of 100 external users running jobs on the machine. And the machine is currently running at about a 25% load factor. So 250,000 cores on average are in use. This isn't the only SpiNNaker machine. We've been loaning and selling SpiNNaker boards around the world, and there are around 100 systems in use in several countries around the world. Some of these systems are smaller boards with 4 packages on, and they're useful for training and small-scale robotics. Most of them are single 48-node boards, and one of those boards can support a brain of the scale of a small insect, and there are a few multi-board systems around. And we recently delivered a couple of SpiNNaker boards to the Beijing Academy of Sciences, so there are SpiNNaker machines in Beijing in operation. Now, what can these machines do? Well, they were designed to support computational neuroscience. And probably the most interesting model that's been demonstrated on SpiNNaker so far is a model of a cortical microcircuit. This represents all the neurons and synapses in a square millimeter of cortex. And the same model has been run by its developers at Jülich in Germany on supercomputers, and it's been run by us on SpiNNaker in Manchester. And at the beginning of this year, we announced that we had this model running in real time, and this was the first real-time version of this model. So we were running on SpiNNaker faster than supercomputer and GPU models. The model contains 77,000 neurons, 285 million synapses, and it computes with a 0.1 millisecond time step. So the best versions before this were the high-performance computing model, which ran with a 3 times slowdown, and a GPU model, which ran with a 2 times slowdown. And in the next phase of the Human Brain Project, we're going to scale this up to a multi-region model. The current model uses only a small fraction of the machine, so we can dedicate more of the machine to running multiple versions of this model that are connected as multiple regions of the cortex. And at the moment, this model replicates accurately measured biological firing rates, but at present it has no function. And a major goal of the next phase of the Human Brain Project is to try to begin to understand the function of this key cortical microcircuit. At a more abstract level, we have also demonstrated that we can implement stochastic spiking neural networks that will solve constraint satisfaction problems. These are the hard class of problems in computer science. And the example shown here is Sudoku. It's a simple constraint satisfaction problem, but it has good visual properties. Similar problems include map coloring and icing spin systems. This work was motivated by earlier work carried out by Wolfgang Mass's group at TU Graz in Austria. We ported this across to SpiNNaker, used more realistic biological neurons, and showed that with appropriate stochasticity, these networks were still highly capable of solving constraint satisfaction problems. So that's a couple of examples of things that have been done on the SpiNNaker platform. The silicon used in SpiNNaker is now nearly 10 years old, and the technology is much older than that. So during the last 7 years of the Human Brain Project, we've been working with collaborators at TU Dresden in Germany to develop a second generation machine. So that leads on to my final topic, which is SpiNNaker 2. The objective with SpiNNaker 2 is to continue the principles that we've learnt with SpiNNaker 1, make some changes based on what we've learnt, but also use more advanced CMOS technology to scale up the system. So whereas SpiNNaker 1 has 18 cores on a chip, SpiNNaker 2 will have 152. All the other system parameters have to scale up proportionately, so we need larger memories attached to this and higher bandwidth interchip links. You can see an abstract floor plan of the chip here. It's dominated by the processing element, which is laid out as a quad processing element, so 4 PEs in a block. And most of the chip area is taken up by these processing units. Their memory is local. You can see the memory blocks shown on this picture. And they communicate through a NOC. The other large function is the SpiNNaker router, which is very similar to the router developed for SpiNNaker 1, where every neural spike becomes a small packet, and that packet is routed through a multicast network to other chips in the system, where the constraint is it has to arrive at all the other chips in a very large system in a small fraction of a millisecond to maintain biological real-time performance. The QPE component has been laid out in detail, and it has been fabricated on small-scale prototype devices that we have in the lab, and the full-scale chip is scheduled to be taped out towards the end of this year. If we look at the processing element, then we can see some of the lessons that we've learned from the first generation machine. So firstly, we're making extensive use of dynamic power management so that every PE can individually operate at a higher or lower clock frequency and voltage. So peaks in the processor load can be absorbed by switching up within a single time step to increase the throughput to roughly double the throughput of the PE when that's required in that time step. The PEs can share memory much more flexibly on SpiNNaker 1. The abstract model that we built SpiNNaker 1 to support does not require memory sharing, but we found that memory sharing is increasingly useful as we built richer and more complex models. So we're improving that characteristic on SpiNNaker 2. We're also building the chip so that it will support conventional artificial nets as well as spiking nets. And so each PE will have a multiply accumulate accelerator, which will give it near state-of-the-art performance in supporting standard artificial neural networks. In addition, we've identified what are the key functions in spiking networks, and we're implementing accelerators for those. One of the key functions is a source of very high-quality random numbers. These come up a lot in spiking networks, but also accelerating basic exponential and logarithmic functions is also very useful. The processing elements connect through a network on chip, which is relatively standard technology. And then at the lowest level, the silicon uses adaptive body biasing to compensate for variability in process during manufacturing. So this reduces the range of different parameters that come out of manufacturing and allows the chip to be more tightly optimized for performance and energy efficiency, less subject to variability from manufacturing. An example of what can be done with this chip using, in this case, the multiply accumulate operation is demonstrating on a small scale prototype an algorithm developed again by Wolfgang Mass's group at TU Graz called deep rewiring. And the significant thing here is that this shows that with a standard benchmark artificial neural net, the number of connections in the network can be reduced by more than a factor 100 without significantly compromising the classification accuracy. So this can reduce the memory requirements of the network by a factor 30 and the energy required for the network by a factor 100 without significant compromise of classification accuracy. And we feel that the sparse connectivity that characterizes biological networks is an important property that's going to arise increasingly in both biological models where it's inherent, but also in engineered artificial networks. And in the future, this will affect the way that hardware designed to support artificial networks operates. For example, I mentioned earlier that GPUs are particularly good at dense matrix operations. Well, if the connectivity is sparse, particularly if it's down at 1% or below, then the dense matrix model no longer applies, and alternative hardware optimizations have to be found to run those networks really effectively. So I got through the topics in my talk. Just to summarize my key messages, SpiNNaker, the project has been 20 years in conception and more than 10 years in construction. There are 90 or 100 boards with other groups around the world. We commissioned the million core machine in Manchester, and that's now offering a continuous service to users all around the world. The software support for that machine comes from the EU Human Brain Project, and the SpiNNaker platform will be integrated into the HBP eBrains infrastructure over the coming years. In parallel with the work on SpiNNaker and similar neuromorphic systems, there have been huge advances in industrial AI, which use an older non-spiking form of neural network. And those two developments have run in parallel, but largely independently up to now. But there's a growing expectation that spiking neural networks will have something to offer to industrial AI, and conversely, that the great progress in industrial AI with deep networks and so on is almost certainly telling us something about how the brain works. So there's an expectation that there'll be cross-fertilization from these two threads, which so far have run largely independently. And spiking networks may contribute in areas such as energy efficiency in industrial applications, but they may also facilitate important processes such as continuous online learning or one or few shot learning, which are very difficult to do with backpropagation trained deep networks. So the future, I think, is very exciting from where we stand now. There's a term that's being used inside the Human Brain Project for this kind of cross-fertilization. It's called BioAI. So AI applications that have much more biological input into them than with conventional artificial nets. And in this area, we think that SpiNNaker is an ideal research platform because its neuron and synapse models are all implemented in software. So it's a very flexible platform. You certainly compromise energy efficiency for the flexibility, but for a research platform, we think that's a good compromise. And as the community comes up with new learning rules, particularly in the BioAI area, they're relatively easy to implement on SpiNNaker because they require quite a small and localized change in the software. So SpiNNaker will do a good job in this area, and SpiNNaker 2 coming out towards the end of this year will be 10 times better, significantly more than that on applications that are well matched to its accelerators, but basically starting from 10 times better. The graphic on the right of this slide shows some interesting numbers. the vertical axis is the energy for a synaptic event. That's the energy required to pass one spike through one synapse. At the bottom of the graphic is biology, which uses about 10 to the minus 14 joules per synaptic event. At the top of the graphic is a standard supercomputer model of a biological network, which, running a detailed model, uses about 1 joule per synaptic event. If you go to a simplified neural model, then you can bring the supercomputer energy down to 10 to the minus 4 joules, or a tenth of a millijoule. SpiNNaker runs at about 10 to the minus 8 joules per synaptic event. SpiNNaker 2 will be about 10 to the minus 9. And the leading edge analog and digital hardware neuromorphic platforms can achieve about 10 to the minus 10 joules per synaptic event. So there's a huge range of efficiencies. At present, none of our engineered systems are getting close to competing with the biology, but there's still room for improvement in the downward direction. And again, in our view, SpiNNaker is a very good research platform. If you want to deliver a product, then you probably want to use a more efficient technology. But while you're still exploring the solution space for your product, then the flexibility that SpiNNaker offers makes it an ideal platform for exploring that space. And with that, I'll stop. Thank you very much for your attention.
Thank you, Steve. So let's move to the Q&A session. 线上的这个嘉宾有没有直接愿意和这个 Steve 来交流的？可以，你们可以这个在 Zoom 里面的嘉宾啊，可以直接打开这个视频和摄像头啊，就是和麦克风可以直接问。And Steve， 铁军有问题是吧？
你先问吧。
啊，好，我问一个这个线上这个其他观众的一个问题啊。Steve， could you see the chat window, the question?
Yes, I can see both the chat window and
there is
a Q&A window. Are they the same?
Yeah, very long question from Zhan Zhong.
It's a Q&A window.
Yeah.
Yes, I can see the Q&A window. So the question is asking about the SpiNNaker roadmap. At the moment, the major feature in the future on the SpiNNaker roadmap is firstly the tape out of SpiNNaker 2 and the fabrication of the chip. And our collaborators in SpiNNaker 2 at Dresden have received a substantial grant from their local science ministry to build a large-scale machine in Dresden, which will be similar in scale to the SpiNNaker 1 machine in Manchester, the million-core machine. Although because SpiNNaker 2 has more processors per chip, I think they're aiming for a 10 million core machine. And that will be a system called SpinCloud, which will be primarily operated for the use of German industry. They had a lot of interest from German industry in access to the machine when they bid for the funds to make it. So I think that's about all I can see in the next 2 to 3 years in the SpiNNaker roadmap. The second part of the question is talking about singularity, which I think is referring to the AI singularity, the idea that when AI passes a certain point, it will improve itself so fast that its abilities will head off to infinity. I have to say that I am not a supporter of the singularity hypothesis. My view is that intelligence is far more complex than a single parameter that can amplify itself. I think the singularity hypothesis is based on a false understanding of the nature of intelligence, but that's my personal view. So I don't think it will happen in the next decade or another decade or any time. Recommend a few benchmarks for testing how parallel a neuromorphic system is. There's been lots of discussion of benchmarks, and a difficulty with benchmarks is that if you look at the range of neuromorphic systems available today, they have very different characteristics. So in my talk, I talked about the cortical microcircuit. Okay, that's a very challenging benchmark, but I suspect it's a benchmark that the majority of neuromorphic systems simply couldn't run at all because of its parameters. In the cortex, pyramidal cells have approaching 10,000 synaptic inputs, and many neuromorphic systems cannot support thousands of synaptic inputs per neuron. They're limited to hundreds or maybe 1,000. So it's quite difficult finding a benchmark that offers a fair comparison of different neuromorphic systems. Quite a lot of work has gone into this in the Human Brain Project, and there are some very simple benchmarks that can be run on most neuromorphic systems, but it's not clear they're telling you very much about the strengths and weaknesses of those systems, because small systems are relatively easy to run on. You can run them on your laptop or on a small microcontroller. So that the major feature of SpiNNaker is its scalability. So any benchmark that doesn't use scale is not playing to its strength. Okay, so I think the space is too diverse at the moment for a small set of benchmarks to be really useful, although they're useful for doing two-point comparisons. So often if you can run a reasonably rich benchmark on two platforms, you get a sensible two-point comparison, but then you can't run it on the other platforms. And what are the essential characteristics you should worry about in a neuromorphic system? Well, it's multidimensional. So there's obviously performance. Can it run in biological real time? At least one neuromorphic system I know of, which is the Brainscale system at Heidelberg, is 10 to the 4 faster than real time. Okay, but most neuromorphic systems operate at or around biological real time. Energy efficiency is important. As I mentioned in my talk, we've traded that off a bit against flexibility because we're building a research platform. The richness of model you can support is important. How diverse are the set of learning rules? For example, Wolfgang Mass's group at Graz has recently come up with a very interesting gradient descent algorithm for spiking networks called EPROP. Now, we can implement that on SpiNNaker because of the way we use software for learning rules. Intel is having to do, the next generation low-E chip will support EPROP. The current low-E chip can't because of the way it was designed to implement algorithms in hardware, albeit very parameterized and flexible hardware, but not flexible enough to accommodate EPROP. So, so flexibility, I think, is important, but it has to be traded against energy efficiency, which is also important. Another parameter which, given what I said at the end of my talk, I think is important, is the ability to blend conventional artificial nets and spiking nets. And I know this has been an important characteristic of the Tianjin chip from Tsinghua, that it supports hybrid networks. And you heard me mention that SpiNNaker 2 is intended to offer better hybrid support as well. So there are many dimensions to this space, and I've mentioned a few that I think are important, but there are others.
OK， 铁军要提问吗？你把那个摄像头对。
Hello, Professor Furber. So you mentioned that the SpiNNaker software was supported by HBP. So can you give some information for the software that, for example, the Chinese master or PhD candidates, they maybe participate in the developing of the new version in some way to participate?
Yes, the SpiNNaker software stack is all public domain on GitHub, so it's openly accessible. And people who want to contribute to that can access it, and they can access the machine in the usual way. In particular, users who want to introduce new learning rules can do that. A learning rule is implemented in the real-time C code that runs on the machine. Most of the machine configuration software stack is a large Python stack that maps networks onto the machine. It views the machine as a graph and the problem as a graph, and it maps the two graphs together. So yes, so there are opportunities to contribute to this from outside the HPP. In fact, the activity is open. It's not always easy to find your way in, but if people have particular ideas, then we have an email support service to help people do that.
Okay, so another question is for the SpiNNaker. You mentioned the SpiNNaker system can simulate 1% of the human brain or 10 mouse. So where or when that kind of model available and can run on SpiNNaker?
So there are two sides to that problem. One side is having a machine with the capacity to handle, for example, a whole mouse brain. The other side of the problem is how do you generate a model of a whole mouse brain? And there is a whole mouse brain model that has been developed within the Human Brain Project that's available, but it's not available in a form that's easy to map onto the machine. So we are looking at this. It's a scalable model, so you can generate a 0.1% or 1% or 10% mouse brain. Everything can be scaled up and down, but the model doesn't capture the hierarchy that would make it easy to map onto SpiNNaker. So SpiNNaker likes to map problems in a hierarchical way, and currently the mouse brain is fairly non-hierarchical. So we continue to look at this, and we may find a way to do it in the next 2-3 years, but it's not an easy problem.
Okay, thank you very much.
Okay, it's time for our Q&A session. Thank you, Steve. Hope to see you again in the future.
Thank you very much.
Okay.
Bye bye.
非常感谢 Steve Furber 给我们做的精彩的演讲啊。